So we will be continuing on to the next session, which is a plenary session, which will and over to Dr. Kulkarni for that.
So now we have without any break, we will go ahead with our next session, which is a plenary session, and we have Professor Shevgaonkar, who has kindly agreed to talk to us on the, as he said in the morning, I missed one of his things in his CV, that he is by heart he's a good teacher, and he would like to interact with us on this subject of electromagnetic waves, and he will share with us how we can teach this subject in a better way. So without any further introduction, I will hand over this to Professor Shevgaonkar.
Good afternoon. I think you already had a long day, and my slides are not as colorful as you have seen in last two presentations. Well, I'll start with every time the question is asked, that when you undergo a course, what is the use of this course? What is the application of this course? So I will take from when Faraday invented the Faraday law of electromagnetic induction. That time the Queen asked him, what is the use of this Faraday law of electromagnetic induction? So the immediate reply of Faraday to that was, what is the use of a newborn child? No use, right? On a lighter side, he said, well, today you may not find its application, but I can assure you it is going to generate so much of business which you can tax and run your government. And I think that's what is true today. The electromagnetics has created so much of business that people are really making millions and millions and millions of dollars and making really money out of that. Following that, when I teach this course, and I ask again the same question in the context, even when in our pedagogy, ask a question when you were taught the Newton's law of gravitation, right, which is normally taught in the high school. And if some student asks you, what is the application of Newton's law of gravitation? Do you think you will be able to tell any application of Newton's law of gravitation? To my mind, hardly any application of Newton's law of gravitation comes which can explain to a high school student. Except maybe you jump from the window, you will fall down. So don't jump from the window. That's only the application probably you will come to your mind. So the question when somebody asks what is the application, there are some things which find application immediately. There are some things which find implication after some time, after you mature. And there are sometimes may not be applications directly visible to you, but there is something to enjoy. That's the reason I changed my topic, rather than effective communication or teaching course, enjoyable way. How can you teach electromagnetics or electromagnetic waves in an enjoyable fashion? Okay, and that is, in my opinion, when you talk about the course or education, the first object of education is you should first enjoy it. Other things follow; they'll come later on. So, with this in mind, essentially, I'm just going to run through slides and have some frank suggestions, frank discussions, and I'm open to have a discussion in the following way. The first thing which I find in the teachers of electromagnetics is they themselves are not excited about the subject. That's where the beginning is. Many times they go and teach the course because somebody has asked them to go and teach the course. Their first answer is, I never wanted this course. But my management or my head of the department thrust on me, so I'm teaching this course. So if you start a battle with an assumption that you are going to lose the battle, you are going to lose the battle. You will never win the battle, right? So the first thing is you should be first excited. All the people who are going to teach the course, they should keep that in mind. And how do you excite yourself? To listen to the lectures which are very, very inspiring lectures. And one of the ways to do that is listen to the Feynman's lecture. Actually, I got excited in this subject. I also thought initially the subject is a very boring subject, dry subject. But then when I happened to listen to the lecture, which is a video lecture, on television by Feynman. And one of the things which he was explaining was that electromagnetic phenomena is simply a play of charges. You have a charge, and we all know if you are having a charge, then this charge creates electric field. Everybody knows about that, right? But if the same charge is kept in motion, then it doesn't remain a charge. It becomes current. Then we also know that the current produces magnetic field, right? Where the charge produces electric field. So what has changed now? The same charge, when it started moving, it became current. So whether the charge moves or you move with respect to the charge, it becomes a current. So the Feynman was explaining that there is a charge there. You stand here and look at the charge and you see electric field, right? Now I start moving. Charge is not moving, I am moving. But for me, it looks a current now. If it looks to me a current, then I should not see electric field, I should see magnetic field, right? And he explains very nicely in his lectures how the same electric field start looking like magnetic field. You know, when that kind of lecture you listen, you see there is a profoundness in this subject. It is not simply manipulations of equations. It is something which is very profound behind this phenomena which we are talking about. So first thing I would suggest, anybody who is even remotely want to be interested in this subject, listen to these lectures which are highly inspiring lectures. Read through the notes of the Feynman and you will see many of the things just for sake of enjoyment. You will learn lots of things from this lecture. You know? So that is first thing which I say. Teach the subject without a bias, which I already said. Learn the subject without a bias, teach the subject without a bias. Okay. Every subject has some nuances which you have to go through. Every subject has some axioms, some basic assumptions, some principles. And at the end of every subject, you are going to get only a handful of concepts. Nothing more than that, right? So if you start a subject without a bias, with a very clean, open mind, and then if you start seeing these beauties in the subject, you will start enjoying the subject. So start without a bias. This is the second suggestion. Assure the student that it is not a difficult subject. I have seen the teachers for electromagnetism of both the types. The teachers who assure you that this is the subject which is very easy, I understood, you also can understand. We have seen also teachers which presented a subject in such a way that only I can understand and nobody else can understand the word. No? And if you project the subject in such a way that nobody can understand, essentially you are telling student you will never understand it. Because I only could understand this subject. If that is the assumption you start with, how the student will get excited? He gets completely demoralized in this process. No? So first of all, you should convince the student that no, this is a nice subject, everybody can understand, and since I could understand, there is nothing very special about me, so you also can understand equally well and enjoy the subject. Thirdly, use a quality textbook and not some solution keys. It is something very, very important. What is happening today, if you go to, by and large, you go to the colleges, you are buying the texts or the books which are available, which are only from the viewpoint of clearing the examination. There are solution keys which are available. Recently, I was discussing the matter with McGraw-Hill. And they said, sir, but who buys these books? People buy only the books of Technova. I said, what is this Technova? They said, so these are the solutions which are available. And everybody knows from this only the questions are going to be asked. So they solve these questions and that is good enough for the course. I think that's not the way a subject should be taught. Because a subject is not for clearing the examination. Subject is first to learn something. Examination happens to be checking whether you have understood something or not. So a good textbook is, and not a simple key kind of thing, is extremely important for understanding the subject. Next one. Define the objective of the course clearly and tell its application in day-to-day life. Few examples. So first of all, objective should be very, very clear. That if I go to this course, at the end of this course, what am I supposed to do? And this I am not saying only for this course. You see from the pedagogy point of view, you go from the accreditation point of view, the accreditation asks this question for each and every course in the curriculum. It says at the end of this course, what you can do. If you give an answer, no, I will understand the subject. That's not enough. So tell, if I do this, I will be able to solve this, I will be able to solve this, I will be able to do this, I will be able to design this. So this objective of the course has to be spelled out to the student at the beginning. And while explaining the course, keep on visiting this. That look, that's what I said in my first lecture. Now look, that's what we are doing here. So if you keep on referring every time back and forth and keep convincing the people that what objective I had defined, that's what I am following and going through this course, I think the students will always remain connected with that. Give few day-to-day examples, which are very catchy examples, which everybody sees around them. So they start getting connected with the subjects. And after that, I remember this time Uday Kankoji in IIT Delhi, he did a very good exercise. He asked the students to go around and find out where the application of this subject is. And believe me, I think he had an exhibition there ran. The hundreds of students got the applications, which were displayed. So once you told to the student to find the application, they just went around and found the applications which were there in day-to-day life, actually. So you require a link, something like that. If you do not know the answer, say I do not know the answer. And let us find the answer together. Never try to, suppress or don't ask this question, This is a bad question. Every question is a good question. Every answer will be only a bad answer. Every question is a good question. And simple question, when somebody asks, it is the most difficult question to answer. So if you give a talk to the experts, it is the easier way to give a talk because everybody understands almost same language, everybody is on the same frame, they talk the same thing. You give a talk here to a high school student and he will ask you some question, which in his opinion, everybody's opinion might look very stupid question. But if you start thinking about it, you will think, my God, this is not a simple question at all. Let me give an example of this. There is a battery, okay, and there is a two wire which I am connecting, or take this cable. I take this cable to the battery positive terminal and negative terminal. I ask a simple question, there was a voltage here, it's a DC battery. How did this voltage get transferred from this battery to the other end of this cable? Is it a simple question? How many of you think it's a simple question? I repeat the question. I have a battery. Repeat the question. I have a simple battery here. Something like that. Okay, these are terminals. Alright. I'm just putting a cable now. I'm just putting a cable in front of it. Initially, when the cable was not there, this was the voltage which was here. How did this voltage now finally got transferred here? Is it DC voltage I am talking about? Is it a simple problem? How many of you think it is a simple problem? And if it is a simple problem, you have to explain it, how it comes, how it happens. You will see it is not a simple problem at all. It is an extremely difficult problem. And to invoke that, you have to apply the entire transmission line theory. Without that, because as soon as you have a battery and you connect something, this phenomena is not a DC phenomena. This phenomena is a AC phenomena. And if it is an AC phenomena, the concept of transmission lines are built in. And if you really talk a switch which has a very zero connecting time, then you have generated essentially frequencies which are infinite frequencies. Now you ask a question, how the infinite frequencies are going to set up on this wire. So any frequency you take which is not DC, it will send a wave on this. This wave, it will see open circuit on the other side, it will get reflected on that. Right? When it comes here, it again doesn't see the impedance which is matched for this wire, it again gets reflected back on this. This thing keep on happening for all frequencies. Finally, infinite times it will settle down and the voltage will appear probably on the other side of the pedal. Right? So the question, if a high school student would have asked this question to you, either you will say, this is a very simple question, don't ask this. But if you ask this question to yourself and start analyzing it, you will see question is not very simple at all. Think about it. Right? So many times the question appear very, very simple, but these questions are extremely profound questions. And if you think about them, then they will give you a lot more understanding and insight into the problem which essentially you are talking about. So this is something to start with what should be your discipline. Now come to the electromagnetic phenomena. Electromagnetic subjects, normally there is a feeling, there is a notion that this is a highly mathematical subject. That's what everybody feels, right? Now the origin of the electromagnetics is in what? It are the four laws of electromagnetics. There is the Coulomb law, there is the Faraday law, there is the Ampere's law, And there is a conservation, there is no monopoles for magnetic field, so you get the fourth law. So that means the whole field of electromagnetism started from experimental physics. These were not the God-given things. People did experiment, then they found there is a relationship between them. So if something which had a full grounding into the physical experimentation, how can the subject become only mathematical? So problem is you have lost something somewhere. Subject was not like that. You created a mechanism, and in that process, essentially you suppress all the physical understanding and started manipulating getting into your equations without giving the full support which is there built into electromagnetic phenomena. So if you give that understanding, then you will see that the subject will become naturally interesting, because you can connect the physical concepts which are associated with this phenomena. Okay. Second thing which comes is the electromagnetic. That way, if you really look at the phenomena of fields, it is an abstract phenomena. How do you visualize fields? There are various ways to visualize fields. And there is no reason to impose only one way of visualizing fields the way you visualize to the next person. Most of the time what we do, we think that's the way the field should be visualized. If the electric field is there, it should be visualized like an arrow. Why it should be visualized like an arrow? That is one way of visualizing the electric field. If without looking at that arrow, if you can imagine what the visualization of the field is, you should be able to visualize the field that way. Normally, we do not give that kind of liberty to the students. Okay. Now, just to give an analogy, why the visualization of field is not very easy, it is very difficult. There is something called the invisible triangles, concept. So let us say if I ask you to draw the triangles in this room, can you draw the triangles? You can draw triangles, right? You can have that one ray there, one line I can join here, one I can join the line like that. I can see this triangle. These triangles are not visible, but from my imagination I can draw these triangles. But these triangles are the ones which are geometrical triangles. And in 3 dimension, I am used to drawing figures which are geometrical figures, even if they don't exist. Do I have equivalent of this in electromagnetic field or any field for that matter? The answer is no. There is no mechanism which can be sort of mapped to the geometrical figures or geometrical shapes which are there in 3-dimensional space. That means the mechanism which is available to you for visualizing something directly cannot be imposed on the fields. Field phenomena is a very different phenomena for visualization. And you have a mechanism. You can talk about the arrow, where the length of the arrow shows magnitude, the arrow shows direction, and various other ways by which you can show. And if you don't require anything like this, but still you can imagine the field, perfectly it's okay up to you. So the student should visualize the fields on their own, through simple systems, but give them time to do that. Anything new concept which you come, which doesn't look very trivial, very simple, you cannot ask that today I will tell you concept and tomorrow you should be familiar with the concept. It will not happen. They will require some time to really digest this concept. So first of all, give some time for students to really think about it, to visualize about it. Then you give them very simple problems. That okay, this is a problem, look at it. It's a very simple problem. Can you visualize the field for this? Let them come up with that visualization. Let them talk to each other and find out whether their visualization, other person's visualization really sort of can communicate with each other, to match and so on. So you require some kind of visualization which is required. Derive Maxwell's equation from the physical laws. Now there are 2 schools of thoughts about the Maxwell's equations. One school of thought is, and both has advantages and disadvantages. One school of thought is you write down the Maxwell's equation into differential form. Okay. And then you say these equations are God given. And everything follows from there. Right. Other school of thought is no, the electromagnetic phenomena was experimental phenomena. And that's why, so you can write down the physical laws which are originally in the integral form. Then you apply the theorems which are there, the Stokes theorem, divergence theorem, and then from there try to get the differential form. Why I said both have advantages and disadvantages? It has advantages and disadvantages because if I say these are experimental laws, then the exactness in the laws could not be there. Right? You can always say, how do you know this is 1 over r square? Is it 1 over r to the power 2.0001? Should it be exactly r square? Should it be whatever that law is? So as soon as you say this origin lies in the experimental thing, then the exactness you can't justify very easily. If you go to differential form, then you are saying these are God-given equations which are very exact equations. So there is no approximation involved in this. But it sort of loses complete touch with the physical world, because then you get lost into divergences and curls. Good combination would be, for exactness, say that these are differential equations which are Maxwell's equations. You are going to solve these equations, but at the same time don't forget that the origin of this is in experimental physics. So keep on giving the physical understanding of this one-to-one, and if you do that, then you will be able to in a good position, because student can really understand what is going on in this whole system. Use mathematics to get quantitative answers for the qualitative understanding of the concepts. What does it mean? Your logical physical understanding must lead the mathematical derivation. Don't conclude after you get the result, after deriving something. You predict, that's what I'm going to get. What mathematical thing is going to give you something quantitative? I did not know exactly what the quantity would be, but I knew this phenomena is going to come. Right? Take a simple example. When I say Faraday's law of electromagnetic induction, right, or Ampere's law, you take, for that matter, it says E dot dl is equal to the EMF induced is equal to dB by dt, right? As soon as I say E dot dl, if I take along the loop, then I apply the divergence theorem, I see the curl. Now where the curl is coming? This loop, the current is flowing. So wherever this phenomena is there, which is capturing somewhere, I know the curl is going to come somewhere, because that's the phenomena I am physically seeing happening there. When I am saying a charge here and the flux is coming out of this, and I am going to capture this flux somewhere, I know somewhere divergence is going to come. Right? So when I see divergence there, I am not surprised, because in that physical phenomena, I should have seen divergence before I could even write del dot something. But give this feel what the divergence is. And the best way to do that is give some examples. Give some example of day-to-day life. When your basin, there is a choking of the water and the water comes from the basin out. What is this? Divergence. Right? Water is just coming out of that. Divergence, something which is happening. Right? Similarly, you are seeing on the surface of the water, the tree, the leaf falls on the surface of the river. It never flows like that. It goes like that. Ask a question. Sit there and ask a question. That why the leaves started rotating? Nobody put that rotational thing in that leaf, but it started rotating. Start thinking about it. So if you look this phenomena and if you give the example which are there, then these concepts will naturally follow. People will start seeing these concepts. That's what happening in the real life. So whenever we do in derivation also, analysis also, to a class, give a conceptual thought experiment first. Okay, suppose we do this. What do you think you will expect? You will get variety of answers from the students, right? First, logically rule out. Ask them to convince. Why do you think it is that way? Why not other way around? And logically, if they rule out, they will see qualitatively, they will have reached to the answer, more or less. Then you say, okay, now let us solve the equation. And see whether the equation also tells you the same thing. And you will see, invariably, before even final result is obtained from the equation, student will say, yeah, this is what I was expecting. Great. Right? So, for research also, I just want to add here, for the research also, when people do, most of the time what happens, you do something. Right? And you get some result. And you say it's research. Right? I did something, so I got some result. Of course, you will do something, you will always get some result, right? So ask a question, if I have a wire, I just connect some voltage or current to this, it will radiate. Is it an antenna? It's not an antenna. Why? See, if I apply some voltage, it started radiating, so I started calling it an antenna. That's not an antenna. So good research is on your basis of your understanding. You say, that's what I expect. Right? If you get it, well and good. You understood the thing correctly. If you don't get it, even that is good. That means your understanding was wrong. So you refine your understanding and predict again. Till this happens that you predict and you get it. That's what is good research. Right? Not that I tried something, I got something. Invariably in research also I hear an answer from students, lots of students. Why did you try this problem? The standard answer comes, nobody else has done it. My standard answer to that is, nobody else has jumped from the terrace of this building also up till now. Does it mean that you will go and jump from there? You will not. So you have to first say why I am solving this problem. On logical reasoning, on understanding, you should predict, that's what I am expecting from this. Then you do the research, then you solve the problem, and it is going to give you probably more quantitative answer. Unless there are some serendipitous discoveries which nobody knows, and suddenly something happens and you may accidentally find something. But otherwise, research always should go systematically. So the point which I want to make again is, quantitative analysis should support the qualitative analysis and not the other way around. That's what is very important at the course when you teach. Avoid necessary algebra in the course. Okay? Don't do the manipulations of algebra for sake of doing manipulations of algebra. Why I am saying this is, because most of the time you will see that questions are asked, the things which are done are long derivations. Right? Similar problem, little modification, for long derivation. Similar modification, long derivation. Right? Can you do some nice derivation and say, well, with this approximation, this becomes this. With this approximation, this becomes this. This approximation, this becomes this. If you do that, people will get much better feel for the course rather than getting lost into algebraic manipulation. So first of all, we should realize that electromagnetics course is not an algebra course. We are not testing the skills of manipulation of equations. We are testing your understanding of electromagnetics. And for that, as much simplified algebra could be, that will strengthen the understanding of the physical concept. Let them not get lost into the algebraic manipulation. Avoid unnecessarily numerical complications. Right? When you teach the subject. Simple example. If the dielectric constant can be written as 4, it is a lot more easier because invariably you will find a root of dielectric constant to take somewhere. Right? Why to give dielectric constant to 2.9? How does it help whether dielectric constant for the numerical problem was 2.9 or 3.1 or 4? Doesn't make any difference. But you see, invariably the problems are given in such a way that you want very complicated numbers. Maybe these numbers are realistic numbers. Maybe the material which you are using has a dielectric constant. But for understanding concept, what difference does it make whether this was RT duroid or this was alumina or this was something else? It doesn't make a difference. So try to use the numerical numbers and values which are simplified quantities. So students don't waste time in simply algebraic manipulations and calculation. They actually spend more time in thinking the concepts which are behind that. So again I am saying, avoid unnecessary numerical complications. Don't make the problem unnecessarily complicated. Right? At least at that level. Following further. Electromagnetic phenomena is an abstract phenomena. And one of the ways to imagine the things in electromagnetic phenomena is give them mechanical analogies. Because mechanical things people can really imagine very quickly. As I mentioned, the law of triangles, you can always see the triangles very easily. So first of all, you try to see, how can I map this to a mechanical analogy? Can I do that? If I do that, you can really project the thing much better. One of the examples, when I was doing my MTech, and the professor was teaching me the Bessel's equation. Bessel's functions were taught. Now, I asked, where do you find these Bessel functions? So he said, no, this is second order differential equation, you have solutions, which are Bessel functions. So I said, I will write one more differential equation, second order differential equation, which is not solvable analytically. I will also get a series solution for this. Would you call it Shevgaonkar function? Question is, why do we solve Bessel function? Do we see Bessel functions? Or it is something which is just creation of mathematical thing? Give an example. Bessel functions have nothing to do with electromagnetism. Bessel function has something to do with the geometry. Wherever you will have cylindrical geometry, you will end up into Bessel functions. Right? So give an example. Every day you take a shower in your bathroom. Right? Your bucket is full of water. You tap that bucket. You see there is surface gets. What are they? Bessel functions. Right? Now if you tell this to him, I am sure every morning when he takes a bath, he will look at the bucket at least for 2 minutes. What is this? This looks like Bessel function. It looks very impressive. He will enjoy it. And then whenever you talk in the class also about Bessel function, you will try to map this. That's what is happening there. So maybe that's what must be happening here also, inside this. Give this analogy of the examples which are more physical examples and something like that. I'll give you another example. When the concept of phase velocity and group velocity was taught, okay, it's a very, very beautiful, very profound concept of phase velocity and group velocity. And then you ask something that phase moves, with some velocity, and the energy moves with some another velocity, and something, student can't really imagine what is happening. There is a very nice mechanical example which I read somewhere, and I tell in my class. He said, look at phenomena of traffic on highway. Example. Okay, look at this thing. Look at this phenomenon. So there is traffic which is going on highway, and let us say there is a laborer who is working on that highway for doing something. Let us say he is doing a job of painting those strips on that. And just to protect himself, what he does, he puts a small barricade around him so that no car should hit him. Now what happens? Look at this phenomena now, go on the top of a hill and look at this phenomena. Okay, the way traffic moves. And you will see, because he has created a barricade around him, there is a small neck of the road is created there. Since the neck of thing is created there, the traffic has to slow down a little bit, not stop. Slow down a little bit, because there is a bottleneck there. Because the traffic slows down a little bit there is a clustering of cars there around that. Now the car is not stopping, it is moving with 60 kilometers an hour, whatever it is. It must slow down a little bit. So when I see from the top, it looks cars are moving almost with same velocity. Because a small change in velocity, you will not be able to notice from there. But you have a cluster of the car which is around this person who is putting this barricade. But this person is not standing at one point. This person is slowly moving because he is painting and the barricade is moving with him. So what you see from the top, this cluster of cars moves with what velocity? What a velocity with which the person is moving. The cars are moving with what velocity? 60 kilometers an hour. These two are different phenomena. Where is the information? In this cluster, right? That's where you can say this is the bundle of energy which you are going to have there, right? So when you talk about phase velocity, it is the velocity of the car. When you talk about this velocity of the cluster of cars around this barricade, that is the group velocity, right? And group velocity is much smaller compared to the phase velocity. In limit only they become equal, but otherwise group velocity is smaller than the phase velocity, normal there. Once you give this example to somebody, you will start now visualizing things, which are very, very good. So like that, whenever you try to explain a phenomena, try to map a phenomena to a physical problem which he sees around, a mechanical problem. And if he can really get the feel for that, then it will be much more exciting and much more interesting to really use that. Now, of course, we are having a computer simulations to visualize things. So you can give this problem to the computers and computer do the simulations, and they can give you many of the phenomena which otherwise you had to imagine, that you could start imagining and start using a computer phenomena. But a word of caution. Whenever you do the computer simulation for visualization, there are two things. The thing which you learn fast, you forget also fast. The thing which you learn with a great difficulty, you will learn for the rest of your life. So, there also you do computer simulation, but don't straight away jump into computer simulation. First you visualize your way. Then you run computer simulation, say whether this visualization was okay or not okay. That is one. Second problem with the computer simulation is, computer simulation always has many artifacts. And unless you are aware of all those artifacts are, you may get the results which may be completely wrong. And unless you have this visualization in your mind, you will not be able to say whether the result which came from this is correct or not correct. So as I again saying, your concept must lead the result which you are going to get. If that doesn't happen, then many times you may get trapped into some wrong results, right, which are coming from the computer simulation. So the computer is a great tool. It can enhance your visualization, but use this tool only as a support tool, not as a core tool for visualizing the fields, for imagining fields. Do not set unnecessarily difficult assignments and exams. Electromagnetic field is a three-dimensional field, right? The phenomena, nature is always a very simple phenomenon. You see, nature is never complicated. All natural phenomena are extremely simple phenomena. So don't try to make them unnecessarily complicated, right? To impress the students, I can solve this problem, not really required. Actually, in this connection, I find a very, very interesting thing, and many of you who must be associated with IITs, IIT question paper is always very difficult, right? Very, very difficult. One of the professors here, mathematics professor, he made a statement, very interesting statement. He said, are you thinking that these problems are solved by the students who appear in the exam? None of them solve these problems. These problems are only to impress each other. Students solve only simple problems, and because it's relative merit, we select the students who are coming there. I think it's really true. Many times we make the problem unnecessarily complicated just to show that how difficult a problem I can solve. But you cannot solve, right? We had a head of the department in our electrical department here, Professor Pillai. He used to say a very interesting quote always. Don't try to find out what the student doesn't know. Try to find out what he knows. Most of the problem which we set is trying to prove that you don't know this. That's what we have been doing, right? Let's not do that. Let us not make the things unnecessarily complicated. Don't make the exams which are complicated. See whether something is required to understand what is minimally required. Ask those questions. Give practical demonstrations if possible. Now, many times experimental facilities may not be there, but since the electromagnetic phenomena is a very continuum phenomena from very low frequency to high frequency, many of these phenomena can be now seen at optical frequencies very easily. I'll give you a few examples a little later. So, if I look at this phenomena in a comprehensive fashion, if the phenomena cannot be observed at this frequency, maybe it can be observed at this frequency very easily. Maybe it can be observed at this frequency. But at least conceptually, that phenomena can be observed. So, give the demonstration and see whether the person can really get a feel for what is going on, in that. At the end of every lecture, pose a question to kindle student curiosity. Now, if you really look at a teacher, the teacher is a one-man movie. He writes his own script, he directs it, he comes on the stage, he performs it, So it is like every day what this person is doing is he is just creating a movie, or he is creating a serial, Now if you watch a serial, how does the serial end? Serial never ends on any conclusion. So what does serial end upon? The serial ends on only suspense somewhere. Next serial episode को देखिए. I think our lecture should end like this. Explain to this point, come up to this point and say, well, here is a question. Want to answer, know the answer? Next lecture. So now if the person who is really curious, he will come to your next lecture. If you close the serial, then he will not come to your next lecture. So this performance which is required and the thought process which is required, you have to keep on kindling the curiosity of the students. You want to keep on posing challenging questions to them. And if you do that, the curiosity will always remain alive. For the student, they would like to know more what is happening in the subject, and they will come to your class. So keep this in mind, that try to always keep kindling the curiosity of the student in the class. So some exciting examples, some are already mentioned in the class, and some I'll just mention here. That if I ask electromagnetic waves course, and if I ask, tell me what are the few things which you should carry with you at the end of one semester course. Divergence, curl is fine. Which I already mentioned there, for anything which is there. The greatest concept which will carry is the displacement current. Right? This is the current which has actually transformed the complete electromagnetism. Because originally when the laws were defined, the displacement current was not there in that. The displacement current came later on. So, and who gave the displacement current? Maxwell. That's why they are called Maxwell's equation and not the Ampere's equation, not Faraday's equations, because they were all single isolated equations. This displacement current is the one which essentially clubbed all these things together and said the electric and magnetic fields are not isolated. They are really linked together. Think one more thing. There is a law which is called Lenz's law, which is there, and which is just mentioned only in one line. Without even referring back to that, yes, that's why it is put a minus sign there, forget about it. Right? You ask in this Maxwell's equation, which is the stability in the entire system? If the electric field produces magnetic field, and if the magnetic field produces electric field, it's a regenerative process. That means if I start with the magnetic field, I will generate electric field, magnetic field, magnetic without any energy. I'll do this. What stabilizes this? Lenz's law, which says the field which is produced will oppose, and that's why there is a stability into the equation. Otherwise, the equations are regenerative equations. There is no stability into the equation at all, right, into this phenomena. So this law, which is just by putting simple minus sign there, give a meaning of that to the people. That look, this minus sign is not trivial. It was just not put just for sake of it or just by just one liner. If this minus sign was not there, the entire system will be in trouble. You will not be able to have a sustained solution because there is a regenerative mechanism which they built into this. So put that phenomenon into it. Characteristic impedance. Another great profound concept. Right? Why is it a profound concept? When you deal with transmission lines, and why it fascinated me always, characteristic impedance is this. When you deal with transmission lines, your transmission line you model by the inductance and capacitances. You say this line is a lossless line. This is what you model with. And then when you get a parameter for the structure which is purely inductive and capacitive, which is purely real, which is purely resistive, right? Shouldn't you get completely, amazed by this phenomena? There's something which came from the element which were completely lossless element, gives you a parameter which is characteristic parameter of the structure and which is purely resistive, that means it can consume power. Right? So this phenomena of characteristic impedance and the associated thing along with that you would have the impedance and then you have reflections coming because of the impedance mismatch, and then you have what is called the impedance transformation and impedance matching at high frequency. When we talk about, as in the morning Dr. Ramchandran mentioned, it actually covers half the phenomena of electromagnetism. And why this should be taught? I fully agree with Dr. Ramchandran why this should be taught at the beginning. Because you still feel like working with the voltages and currents, but the concept of space is brought into consideration. Otherwise, all electrical circuits are not, space has no role to play. Right? So, a very simple question, very first lecture I asked when I teach this course. You have an op-amp circuit. And if I ask you to design an op-amp circuit of gain 10, what will you do? Very quickly you can do that. You have op-amp, you write 10K here, you write 1K here, I got gain 10, invertible op-amp circuit we got. Everybody is happy about it. Then I ask the next question. Suppose I make this 10K resistance which is there by a wire which is some 1 million kilometer long. I can do that, right? I want only 10K. So if I use carbon resistor, the size is this. If I use simple copper wire, I will require some thousands of kilometers. So if I take my op-amp and replace the 1K by a carbon resistor and 10K by this 1000 kilometer wire, will circuit work? Electrically, the answer is yes, it will work. Why? Because the electrical value of that is 10K, which is absolutely correct. But in practice, it will not work. Why? Because the space has to be brought into consideration. Without bringing the space into consideration, the circuit analysis is not complete. So the beginning of your phenomena of transmission line or all that is that space should start playing a role into this, albeit in one dimension. And once you get a feel for how the space behaves or how the space functions, how the space impacts the analysis of circuit, then you try to expand it to 3 dimension. That's what was happening in 1 dimension. Now look at what will happen in 3 dimension. So this phenomena which we talked about here is a very, very profound phenomena, and first students should get a good feel for this phenomena, the role of space into the circuit analysis. If that happens, probably things will become a lot more interesting and attractive. Skin depth, of course, certainly somebody mentioned in the morning, the skin depth phenomena is a very interesting phenomena. You mentioned that, right? Yeah, so did I mention that? So skin depth is a very interesting phenomena. That what skin depth does actually, if you really ask students to really think about it, the skin depth says the resistance is a function of frequency. Earlier resistance was never a function of frequency. The capacitance and inductances were, the reactances were, but the resistance was not. This says now the resistance becomes a function of frequency. Then you ask the student to see if that happens, then what happens to your circuits. Start imagining when the frequency is increased, what will happen? The same thing which was there. Give the example which are more dramatized. Because again, as I said, your curiosity has to be kindled. So, and this should come into the thinking of the students before they do anything. They should ask this question in their mind. Is it okay? Because that's what was projected to be. So if you have a very exaggerated example, if you give to them, you will see that they will remember this. Let me give one simple example. Let's go, I want to go to high frequency testing. Right? I have a circuit here. Normally I want to measure the circuit performance in open circuit condition. So input impedance of the circuit is, let's say, very high. Right? Almost infinity. I take my cable, connect to the circuit, connect to the oscilloscope, measure it. Will it work always? Dramatize it. So student, they should get really scared, oh my god, something will seriously go wrong. So I am having, here I am in open circuit. If I am operating at a frequency where this length happens to be lambda by 4, then this open circuit will transform to short circuit. So what oscilloscope is measuring? It is measuring condition under short circuit condition, right? Not the open circuit condition at all. So what you wanted to measure and what you actually measure are completely different. Open circuit to short circuit and short circuit to open circuit is a very dramatized way that from zero current to infinite current is going to flow, right? In reality, it may not be infinite current, but still the current may be very large. Once you alarm them with this might happen. Be assured. When in laboratory, whenever they choose a cable, they will think about this. Should I connect this cable or not connect this cable? It should come into your continuous thinking all the time and at the back of your mind to the students and the faculty both. I remember when I used to work in Gauri Bidnur, in radio telescope, we were building radio telescope. And we were engrossed in so much about this, the vocabulary which we use for this. That it was a wild field, and one day there was a snake, which was there. So somebody asked, how big the snake was? So he said lambda by 4. Because the lambda was 30 meter lambda, was so much engraved in your mind that in talking in terms of lambda was much easier than talking in terms of meters. Because you had a good feel for lambda. Right? Create that situation to the students. So give them the phenomena and the problems. So that at the back of their mind, they always start thinking that. Start mapping, what is happening into this. So skin depth is something very interesting. Surface current. This is the phenomena which is a completely hypothetical phenomena. It makes the life much simpler. But you ask a question, why surface? Where do you find surface current? Should you find surface current in reality? And you will see, no. It is an abstraction of some of the things when the skin depth becomes almost zero. The current flow appears to be happening on the surface, so you can call it a surface phenomena. Right? Let us not get lost into that, because as soon as you do this, surface current is related to the magnetic field. Right? Whereas for having a current, you require electric field. Suddenly, how can you have a change from electric field to magnetic field? Ask students this question. Let them really probe about it. Think about it. Right? And do that. So, surface current is another phenomena. Free space impedance, another great concept. That if I look at the space which is nothing, and you say this has an impedance of 377 ohms. Ask student to think about it. What does it mean? What is the 377 ohm actually we are talking about, right? So it will give them a lot more thinking into that direction. Phase and group velocity, I already given an example. One of the concepts which people have misunderstood by large number is the polarization, right? This concept is a very beautiful concept, right, which is associated with actually vector nature of electromagnetic fields. All other parameters which you have are all scalar parameters. This is the parameter which captures the vector nature of the field. So polarization, it should be explained. Total internal reflection phenomena, again amazing phenomena, right, which you see, and if you see from electromagnetic point of view, you will get much more profound understanding of what is happening. It is not simply the ray of light is going and getting totally reflected and so on. You will get much better feel. Modal propagation. Modal propagation is a transformative way. It is simply saying that now the electric and magnetic fields have to travel in some discrete patterns. It is not a slow change from one distribution to another distribution. This discrete nature, right, which is imposed by any bound structure, actually is the phenomena which is called the modal phenomena. Now, if I give you a simple metallic waveguide and ask you to visualize the fields, it will be very difficult for anybody to visualize. But as I mentioned, since the electromagnetic phenomena is a very comprehensive phenomena, I can visualize this very easily inside optical fiber, where I can put the light at visible frequencies. There also the modes are going to propagate. I can literally take the field distribution, project it on the wall. I can see this pattern, T10 or whatever, HE11 or T, whatever distribution I talk about. Show these examples at those frequencies where this distribution can be seen very, very easily. And today, looking at the optical frequencies and so on, right, it looks very, very interesting. Pointing vector, right? Pointing vector again is a concept which is an extremely great concept. Okay, and I want to give an example which again Feynman talks about, and look at an example which is very easy. He says, take a simple example which we all know. If you take a capacitor which is charging, tell how the energy moves in the capacitor charging. Right? Take a very simple question. So you have a capacitor, you are charging on this. There is a positive charge, there is a negative charge, which is moving. Capacitor is getting charged. How is the energy getting stored on the capacitor? Is the energy flowing this way? How many of you feel the energy is flowing this way? Because the current is flowing this way. Positive charge is moving, but the current is flowing. Right? Is the energy flowing this way and getting charged and getting accumulated on the capacitor? Then how is it flowing? That's what the question the Feynman asked. Simple question. As I said, the battery question was very simple. This question also is very, very simple. How does the energy? So you can ask a question. As soon as I put a positive charge here and negative charge here, where is the energy? Is it in the charge? Is the energy lying inside the charge? Where is the energy lying? In the field. So you are having, as soon as I have this, I have the energy, the electric field, which are there like that. Right? Now this charge is moving. So if the charge is moving, it is current. So it has a magnetic field also. How the magnetic field is? If the current is flowing this way, how the magnetic field will look like? Current is this way, around the current. So the magnetic field goes like that, around this. Now Feynman says, apply pointing vector. Because pointing vector tells you the flow of power, flow of energy. E cross H, if you take, that's where the energy is flowing. So where the energy was? Energy was somewhere everywhere in the universe. You have electric fields, you have magnetic fields. And if you ask, what is E cross H? This is E, that's H. So E cross H is perpendicular to both of these. This. So how the capacitor gets charged? Not this way, this way. When you hear this, I mean, you get half the romanch aa jate hain, no? My God, no. It is such a thrilling experience to really see this. The understanding which we had about it was so wrong, completely wrong. And simple things like can really give you a great insight into the problem, into this. There are many hypothetical cases which people have worked out what they call is pathological problems, where this pointing vector concept doesn't work, but they are cooked up problems actually, and they are DC problems. But it has so happened that for AC signals, the pointing vector up till now has never failed, though there is no rigorous proof also for it. But look for the examples and show that every time when you try to do this, look at this quantity, and once you got this tool in your hand, without worrying, just look at electric field and magnetic field and just take E cross H, and it will give you the way the energy is flowing into the system. Extremely profound concept which you can really get. Then comes finally the example which I give, again high frequency, is the radiation pattern. Now radiation pattern, when we talk about, just like all of us are very familiar with the dipole antennas, okay, and I ask somebody to draw a radiation pattern of a dipole antenna, okay. We all know dipole antenna has a radiation pattern. This is a dipole, this is a radiation pattern, right? Somebody was asking, there are two lobes in the radiation pattern, okay. What the radiation pattern tells you? It tells you the relative distribution of field or the power flow as a function of angle from this antenna. So if I had this antenna here, it says this direction no power goes, maximum power goes in that direction, right, and so on. But this antenna is circularly symmetric. So I see this pattern, this direction is maximum. When I move anywhere in this plane, this maximum goes to 0, maximum goes to 0, I get that pattern. But is it like there are two things here? It's not. So what is the radiation pattern? The radiation pattern is a three-dimensional solid like apple. Tell this to the student. It is not this. First you imagine radiation pattern as a three-dimensional solid. And then you ask a question, every time I cannot draw a three-dimensional solid very easily. So what I do is I cut this solid in different planes, sections, and I show you only sections of that solid. So I took the apple and I cut it vertically, I see this. If I take the apple and cut it horizontally, I will see this, right, which you can call as E-plane radiation pattern or S-plane radiation pattern and so on. But the thing which you should do is that ask the people to imagine this thing as a three-dimensional phenomena, because that's the way the radiation pattern actually looks like, right? And one of the things what people completely wrong is that suppose I take a simple antenna array, for those people who work in antenna array, it has a radiation pattern which is something like that, it's a long antenna array. If I steer the beam, the antenna beams get steered like that, right? And in this process, this beam width increases significantly. So here is the narrow beam, and when I tilt it down, the beam becomes very, very large. Now if I ask, very simply, if I go by this way of defining radiation pattern and ask which of the antenna is more directive, the beam which has narrow beam, that antenna should be more directive, right? It has more focusing power. So that means by this, if I define this way, this antenna is more directive when the beam is here, and when the beam goes there, it should become less directive, right? It is exactly wrong. And why it is wrong? Imagine this pattern into 3 dimension now. So if I look at this pattern in 3 dimension, it is symmetry is around this. So how does it look like? 3 dimension. It looks like a disc, right? So if I look at a solid angle, it is solid angle of a disc. If I look at this pattern and revolve it around antenna, how does it look like? It looks like dumbbell, right? So if I ask what is the solid angle in a dumbbell and what is the solid angle in a disc, you will see solid angle in a disc is much more compared to solid angle in dumbbell. So this antenna is more directive than this antenna. But if I had not told student to visualize the three-dimensional structure, immediately they would have concluded this antenna is less directive compared to this antenna. So again, what we are saying is, give the comprehensive picture and ask the student to imagine into 3 dimensions, because this is the phenomena which is the electromagnetic phenomena in 3 dimensions. And if each one has its own way of visualizing it, you will see conceptually at least something will never go wrong. Numerically something may fail, he may get a wrong answer. But if he has done conceptually everything correct, even if he doesn't get the right answer, doesn't matter. No, it's still worth it. Right? So that's what we have to build in the students. We have to inculcate that habit in the students. And that's what basically this course is supposed to be. If we do that, I can assure you, now no student will bunk your classes, nor you will get bored by teaching this course. Because every time there is something new which you will learn yourself, student will ask questions which you will answer, you will get excited, they will get excited, and things will become very, very interesting. So let me stop here. Thank you very much for this. And if anybody has any remarks or questions, I am very open to listen to your remarks. Yes. That's what I am saying. There is no proof there. Nobody has proved that that's the way the power flow is. The pointing vector is more like a statement that E cross A should give the power flow. So, but you know, there is also but there are some explanations which physics people try to give in there. There is a magnetic field and there is the electric field. One can ask a question even why DC magnetic field is there, what is sustaining the DC magnetic field. So maybe there is a current associated with that, you know, something like that. So net power flow may be 0, but instantaneous power flow is there. But that is only a very conjectured way of looking at things. There is no rigorous proof which says that the pointing vector rigorously says that that should be the only way of my power flow. There is no way there. Maybe somebody else can add. That's what my understanding is. But Dr. Iyer or anybody who work in this can add to this. It will be good for everybody.
We define the time dependence should be.
Huh?
For power flow,
Yeah.
time dependence is necessary or it is not?
Average time, no. Instantaneous is not necessary. Instantaneous, if you have E cross H, you should get a power flow, instantaneous power flow. Right? If you take average of that, then whatever time harmonic you take, average value, you will get that, that quantity. You get by a conjugate and so on. But otherwise, pointing vector doesn't say that it should be time dependent. It should say E cross H should give you power flow at that location. That's what it says. Instantaneous power flow. Right? Uday, is it right? Yeah.
I have into a normal simplest way you can understand, because like I have a small copper strip and I round it as a spiral.
Yeah.
So sometimes it's for beta material. Can you just simply explain why?
Okay. So these are periodic structures.
Yeah.
So basically, when the periodic structure is there,
Yeah, exactly.
right. So periodic structure, the wave propagation you have to really analyze. In the periodic structure, what happens. So one of the ways is, if you are having a periodicity into this, the quantum phenomena will start showing into that basically equivalent, because you are an electromagnetic wave, but basically you will get some kind of a band gap kind of effect which will take place. So this is a property of very periodic structure which you have, which makes the medium dispersive medium, right? And in that process, whatever you are talking essentially will happen, right? Because the wave vector now will become frequency, omega k diagram will change, and so on, right? But that has to be analyzed. Though in concept you can say that, because that's what you see in crystalline materials, that the electron tries to move it, and electron also is a wave. So when it moves into periodic structure or crystalline material, it has this phenomena of band gap. Same kind of phenomena will start showing here also in that process.
But you also kind of can change this.
It actually depends upon the structure. It depends upon the structure. Yes, you have the resonating loops also, right? And the dipoles, you can have a combination of these two. So both quantity can change in principle. Yes, effectively. That's correct. But this question will not come to the normal teaching class. This is a research question which in the morning which people were saying. Yeah, sure, absolutely. You're right. Yeah.
Sir, I don't have a question, but there are a lot of students, so I wanted to share one lighter moment.
Sure, please.
Way back 2002, I think, when you were teaching in IIT, I was staying in one of the hostels and I was working in Samir there. And I think you were teaching electromagnetics to a lot of students. So they always used to call you Shevgaonkar.
I'm very happy with that.
You used to do so much of heart and soul in teaching that subject, which you do so today also after so many years. I was wondering how you could maintain that enthusiasm when you are moving so much in the ladder of administration. But we are very happy to see that the teacher within you is still.
Yeah, I still get excited. But I'll tell you, I'll give the credit of this to the students. Because even after teaching this subject for so many years, every class, at least one question comes from a student, which I have not thought about. Right? And it forces me to think, yeah, there's a very nice way, I never thought about this. Why this fellow thinks that way? It gives you much better understanding of the subject. Actually, one of the students asked me, I still remember that question, and I did not have immediate answer to that. That when I was talking about the waveguide fields, the waveguide field, if you look at the TE10 mode, the waveguide field looks like that. These are the magnetic fields, okay? These are the magnetic field loops, something like that. And electric fields are here, right? So these are the electric fields. Okay. And I was explaining to them that if you want to visualize the fields, what you do is you freeze your time and look at the phenomena of magnetic field and electric field. So I gave an analogy, that look, this is like a railway train. So these are like railway compartments, and these are the connecting pins which are there, compartment which are there. And then after you get this visualization, then you start your clock and then starts moving, right? The train starts moving. That's how the electromagnetic fields move inside a waveguide. I left at that. Somebody raised their hand. He said, sir, but in this case, you ask us to visualize this, but for this magnetic field, what is the current enclosed? Because for supporting magnetic field, the current has to be enclosed by that. Right? Now, of course, there is no conductor there, so conduction current is ruled out. So there has to be electric field there. Right? But electric field, if you see by symmetry, whatever is the positive current, electric field here, exactly negative field is there. So if I take a loop, then the electric field is also there, zero there. So for a moment, I also was, taken aback. Something has gone wrong, while explaining this. So I said, okay, let me think about it. I'll come back to you. As I said, don't say it's a rubbish question. It was not a rubbish question. It was a good question. So I said, I don't have answer. I'll come back to you. And I thought about it. So tell me now, what has gone wrong in this process?
The movement of charge.
So what has gone wrong in this process? The movement of charge means what? Everything is moving now. No, when somebody asks this question, okay, these are the magnetic field, electric field, and what is this thing? No electric field, net electric field is enclosed by that. Right? So how the magnetic field is supported? So magnetic field is supported by what? Rate of change of electric field, not by the electric field. And once you freeze time, the rate, where is the rate now? The rate is also not there now. So this thing, but then once you start thinking about this, then you will see, that your Ampere's law, when you modified it by just putting dt by dt, was not a trivial change. Because now what you see in physical term, what you will see is that the magnetic field which you are going to see at that location would be the electric field will be there, which was there at that location at some time before. Because every phenomena is moving now. It is not a stationary phenomena anymore. So when you are talking rate of change of phenomena, essentially the whole thing is moving in time varying fields. So this was the phenomena which was not here at that instant of time. It was here. So if you try to sort of map back the Ampere's law, you will find it becomes very difficult now to state Ampere's law in terms of displacement current. In conduction current, it was very easy to do that. But this came from a student. He forced me to think that no, this is not right. Something is missing here. We could understand better. That's what will happen. So students should be given the credit for this because they are the ones who keep asking questions, which keeps us on our toes all the time. That's what it is. Yes. You read this Feynman, beautiful explanation. He really shows you by V cross B and all the analysis, and he shows that the same electric field will start looking like a magnetic field.
You see, Prof, Austin and Loren have put a question in their book that there is no such thing as magnetic field. What you call magnetic field
Correct.
is an electric field in a
Moving frame.
in a wrong frame.
Wrong frame, okay, all right. Not even moving frame, it is wrong frame. All right, yeah, absolutely. So for him, there was nothing like a magnetic field because just a matter of change of frame of reference. So if you are having a moving frame, the thing will start looking differently. So read that, you will really enjoy it if you are interested in that. I can explain to you in a very short time, but just read this.
Another question, Prof. We use Gaussian surface to find the fields around the source.
Yeah.
Now, if you have a dipole,
Yes.
you put the center of because the dipole is analyzed in spherical coordinate system, you take the Gaussian surface with the center at the center of the dipole, take a sphere, total charge enclosed in that sphere, the field everywhere should be zero.
Yeah, but it's a time varying phenomena. It's a time varying field. It is not a. So again, it's related to a rate of change. And after that,
But this would apply to even static dipoles.
if you take static dipole, okay, come for Maris, yeah.
So static dipole, Gauss test total flux coming on, not the total flux. You see, my interpretation of this is.
Listen to this. Yeah.
My interpretation of this is that the center of the dipole cannot be treated because in the limit we are allowing this thing to go to infinity. 2qd, even the whole thing, when the whole thing goes to infinity, 2qd remains a finite constant.
Hyper moment.
Yes.
Okay.
So you cannot say that this limit is an unconditional limit. It is a constrained limit in which the finite value of moment has to be taken into account, so that for each charge of the dipole you have got a sphere. Those two spheres in the limit cannot be brought and concentrated
At the same location. At the same location.
Yes.
Okay. Yeah. Because of displacement between these charges, that's what it is. But I'm not okay. But okay, we can have a debate on that. Question is open. All right. All right. So thank you very much. And thank you. Thank you.